Okay, then welcome everyone to the last session for today. We are looking at quantum cryptography. And the first talk is on public key encryption with secure key leasing. And Rio Nishimaki is giving the talk.
Sorry. Oh, thank you for the introduction. I'm going to talk about public key encryption with secure key leasing. This is a joint work with Shuita, Fuyuki, Shota, and Takashi. This is a brief summary of our work. We introduced a new notion called public key encryption with secure key leasing, and we achieve it from standard public key encryption. We also extend the notion to the attribute-based encryption and the public key functional encryption setting, and achieve them from standard ABE and public key FE, respectively. Okay, so first let's see the functionality of public key encryption with secure key leasing. First of all, it is hard to prove that we delete digital information since we can keep a copy. We can copy classical information. Let's consider the following situation. Bob borrows a decryption key from Alice. And at some point, Bob claims that I returned your decryption key to Alice. However, it is hard to prove that Bob deleted the decryption key because he can keep a copy of the decryption key. In general, it is impossible to achieve secure leasing by classical cryptography. However, quantum mechanics enable us to prove deletion or preventing copy protection. So let's see the functionality of public key encryption with secure key leasing. We need to achieve this primitive. We need the power of quantum computation. So Alice generates a public encryption key and a quantum decryption key and a verification key. Here, a verification key can be public or private, but in this work, we consider private verification key. Bob borrows a decryption key from Alice, and someone sends a ciphertext to Bob, and then Bob can decrypt the ciphertext. After that, at some point, Bob returns the quantum decryption key to Alice, and Alice checks whether the returned decryption key is valid or not by using the verification key. If the returned decryption key is valid, then after that, even Bob received another ciphertext under the public encryption key. Bob cannot decrypt the ciphertext anymore. This is PKE with secure key leasing. There are a few previous works. Single decryptor encryption is public key encryption whose decryption keys are quantum states and copy protected. However, to achieve this strong cryptographic primitive, we need strong cryptographic assumptions such as one-shot signatures and extractable witness encryption or post-quantum indistinguishability obfuscation. In secure key leasing, Kitagawa and myself introduced the notion of secret key functional encryption with secure key leasing and achieve a bounded collision-resistant scheme from one-way function. And in general, unclonable cryptography implies cryptography with secure leasing. So single decryptor encryption implies public key encryption with secure key leasing, which can be achieved by post-quantum indistinguishability obfuscation. So our main question is, can we achieve public key encryption with secure leasing from standard assumption? If we assume indistinguishability of obfuscation, we can achieve this primitive. But our question is whether we can achieve this notion from standard assumption. And the answer is yes, we can achieve this primitive from standard public key encryption. So let's move to how to achieve public key encryption with security key listing from standard public key encryption. Before I present our construction, I'm explaining the security notion for public key encryption with secure key listing, which is called security against key listing attacks. The challenger generates a public encryption key and quantum decryption key and the verification key. The adversary receives the encryption key and the quantum decryption key. In the indistinguishability case, the adversary sends two plaintext to the challenger. And the adversary can send a possibly malformed decryption key as a verification query. The challenger answers whether this queried decryption key is valid or not. And if the adversary sends a valid decryption key and the verification key, then the challenger generates a challenge ciphertext and sends it to the adversary. In the indistinguishability case, the adversary guesses which was encrypted, plaintext M0 or M1. And in the one-wayness case, the adversary tried to recover the entire plaintext. Here is roadmap. So we want to achieve indistinguishability notion against the key listing attack from standard in the CPA secure PKE. First, we construct a one-way carrier secure PKE from in the CPA secure PKE. And then we upgrade one-way carrier secure PKE to in the carrier secure PKE. Let's see the first part from next slide. The construction idea is very simple. We use two key pairs of standard public key encryption. The decryption key is superposition of two decryption keys, DK0 and DK1. And ciphertext consists of two ciphertexts of the same plaintext M and two different encryption keys, EK0 and EK1. We can decrypt this ciphertext by applying decryption key in a superposition way. And the decryption results are the same because these two ciphertexts are the encryption of the same plaintext. So the decryption key does not collapse even after we apply the decryption key. And we can also verify the decryption key by using measurement by this projection, which is generated from two decryption key, DK0 and DK1. So before I explain how to achieve a full one-way carrier security, I explain how to achieve half one-way carrier security, which means the adversary wins the game at most half plus negligible probability. Okay? So we can consider the following trivial strategy. The adversary measure the decryption key and get DK0 or DK1. Okay? By measuring this superposition decryption key, we can obtain DK0 or DK1. And if we use this strategy, the adversary can pass the verification with probability half. And it can also break the security because the adversary can recover, can decrypt CT0 or CT1 by using DK0 or DK1. And actually, this strategy is optimal. We can show this. But the big question is how to show this strategy is optimal. Actually, this task is quite non-trivial. And we show this by using a new security notion called consistent or inconsistent security. So before To achieve one-way carrier secure PKE, we use COIC carrier secure PKE. Precisely speaking, we need a stronger version of COIC security, but to make this presentation simple, I use the normal notion of COIC security in this talk. Okay, from next slide, I'm explaining how to achieve one-way carrier secure PKE from this new security notion. Oh, sorry. Maybe back to, sorry. So first I explain what is consistent or inconsistent security. The challenger generated two key pairs of public key encryption, DK0, DK1, and EK0 and EK1. And the adversary received a decryption key superposition of DK0 and DK1, and also received two encryption keys, EK0 and EK1. And the adversary can send a verification query as into-carrier security or one-way carrier security. And after the verification query, the adversary sends two plain text to the challenger. Then the challenger flips two random coins, A and B, and generates ciphertext CT0. It is encryption of M sub A. And it also generates ciphertext CT1, which is encryption of M sub A XOR B, which means if B is equal to 0, these two ciphertexts are consistent. However, B is equal to 1, then these two ciphertexts are inconsistent. The challenger sends both ciphertexts to the adversary, and the adversary guesses bit B, which means the adversary tries to distinguish these two ciphertexts are consistent or inconsistent. This is a COIC security. By using this security notion, we can prove that the simple construction satisfies one verification query and half one-way carrier security. So here, I show the security experiment of one-way carrier security for the simple two-key constructions. The adversary receives the decryption key, superposition decryption key, and can send a verification key query once. And if the query is the adversary sends a valid decryption key, then the challenger sends two ciphertexts, which is encryption of M. First, we slightly change the security game. First, we defer the measurement of decryption key. By using the deferred measurement principle, this does not incur any difference. And next, we relax the winning condition. We choose uniformly random plaintext M tilde. And if the adversary output M or M tilde, then the adversary wins. This just increases the winning probability. Next, we can apply COIC security here. Originally, CT1 is encryption of M. However, now CT1 is encryption of M tilde. We can even if we change ciphertext CT1 like this, it's indistinguishable due to the COIC security. And lastly, we measure the query decryption key by using a computational basis. Then, if the decryption key is valid, the measurement result is DK0 or DK1. In the last game, if the adversary wins the security game, then the adversary output plaintext M or M tilde. And by using measurement, we can get DK0 or DK1 from the queried decryption key. However, this contradicts to the one-wayness of the encryption scheme, which is implied by COIC security. We can show that we cannot obtain DK0 and M tilde or DK1M by using the Bonnet-Chandler lemma. So we can obtain half one-way carrier security by using COIC security. So this is a high-level overview of our construction. However, of course, half security is not sufficient. We want to achieve full security, full one-way carrier security. We can achieve this by using parallel repetition. Just we use two lambda key pairs of public key encryption keys, and we encrypt shares of the plain text. Then we can achieve the full one-way carrier security. However, here we cannot amplify half security to full security in black box way. We need to directly analyze the parallelized construction to prove the full one-way carrier security. So we saw that we can achieve one query one-way carrier security from COIC carrier secure PKE. And we can upgrade one query one-way carrier security to one-way carrier, many query one-way carrier security by using the notion of one more unreturnability, which I omit in this talk. But note that we do not any additional assumptions for this upgrade. And then we can upgrade one-way carrier security to carrier security by using the quantum Goldreich-Levin theorem. So the last big question, how to achieve COIC security. So we use one-bounded ciphertext policy functional encryption. And actually, this task is also non-trivial. But I omit this part due to the time limitation. Sorry. But interestingly, we use watermarking extraction technique to this construction. And we know that we can achieve one-bounded CPFE from standard ind-CPA secure PKE. So we can achieve ind-carrier secure PKE from standard ind-CPA secure PKE. And we also extend the PKE with secure key leasing to ABE with secure key leasing and public key functional encryption with secure key leasing. And also we can achieve these notions by combining standard ABE or public key functional encryption with PKE with secure key leasing. But, so sorry, due to the time limitation, I omitted these details. Let me summarize my talk. We introduced definitions for public key encryption with secure key leasing. And we also showed that we can achieve this new notion from standard public key encryption. And we also extend this notion to ABE and the public key functional encryption setting. There are a few concurrent works. Anand et al. Introduced the notion of revocable PKE, which is almost the same as public key encryption with secure key leasing. They achieved this notion from LW assumption. So, but we use more general notion from standard PKE. And Basek et al. Achieved public key functional encryption with secure key leasing, but from indistinguishability obfuscation and one function. Sorry, there is a small mistake in this slide. They don't need sub-exponential security for their construction. That's it. Please see our e-print paper for the detail. Thank you for your attention.
So do we have any questions from the audience? So I'm not super familiar with the field. It seems I can give out my decryption key exactly once, and that seems kind of inherent in the technique, right? So if I want to give it to like party A and later party B, that...
No, I think we can. So if once Bob returns to the decryption key to Alice, maybe later Alice can release her decryption key to, for example, Charlie again.
Okay.
Yeah. I think we can apply the well-known non-abelian transformation in our setting because our ciphertexts are completely classical, so we can use the standard non-interactive zero-knowledge technique. So we didn't consider a CCA secure setting in our paper, but I think we can achieve CCA security by using non-abelian technique. Yeah. Thanks.
Okay. Yes.
How long approximately can we hope to get the encryption key, which is a quantum state, from decohering?
Sorry, say it again?
How long can we keep the encryption key prevented from decohering? Because then we will...
Yeah. It's hard to say. But the coherent problem is out of scope of our work, so I cannot say about that problem. Sorry.
All right. Then I think another round of applause, and we move to the second talk of the session.
Thank you so much.
For the second talk, we have another round of breaking and making quantum money, and how to build it from lattices and more. And the authors couldn't make it to the conference, so Barak Nehoran is going to give the talk, but yeah.
Okay, thank you for the introduction. My name is Barak Nehoran, and this work is about some new results, both negative and positive, about how to construct quantum money. Specifically, how not to build it from lattices, and also a new framework for building it from what's called walkable invariance. As you might have noticed, I'm not one of the authors. Since they cannot be here, they have asked me to present it on their behalf. And you can feel free to ask me questions, clarification questions, but for any more in-depth discussion, I urge you to reach out to the authors by email. Oops. So let's start with some background. So the quantum no cloning theorem states that given an unknown quantum state, it is a general unknown quantum state. It's impossible to create two copies of that unknown quantum state. And it's been crucial for the development of the first cryptographic protocols, specifically the protocol of quantum secret key quantum money, which was devised by Wisner in 1970. And here, the banknote is a quantum state that's unknown to the public, and no cloning implies that it's impossible to counterfeit this banknote. The problem is that since only the creator, which we call the mint, knows the quantum state, only they can verify. And it comes with its own host of issues, including the ability to fix deterioration in the banknote and other issues. And this led to Aronson in 2009 to define the notion of public key quantum money, where in addition to the quantum state, there's a public verification procedure, which means that anyone can verify. The challenge with this is that with public verification, this means that you could use brute force to search to find a valid banknote. And specifically, this means that the state is known to the attacker, which violates the premise of the no cloning theorem. And so we need to leverage cryptography on top of the quantum information in order to guarantee no cloning. Public key quantum money has been notoriously challenging to construct with provable security. There have been many proposals over the years, and this is a collection of them. Unfortunately, several of them have been broken, and the rest lack security proof relative to universally accepted computational assumptions. This work makes progress towards understanding the security of quantum money in three different parts. The first result is an attack on a class of lattice-based schemes, which includes a recent candidate by Keshen, Liu, and Shor. And specifically, this attack means that that their scheme is insecure. The second result is positive. It's a framework for building quantum money with something called walkable invariance. And this work gives sufficient conditions to lead to secure quantum money. And it can be seen as abstracting one of the main remaining candidates for secure quantum money due to Farhi et al., the quantum money from knots. And we note that it's an open problem whether their scheme meets sufficient conditions. And the last one is the last part is they give some new candidate quantum money instantiations from walkable invariants, and notably one of them is from is a very natural approach from isogenies. And I'll note that there's one missing piece that we'll come back to later. So first, let's talk about how not to build quantum money from lattices. So lattices seems to be a very natural candidate for use for making quantum monies. And the fork-lower approach to making quantum money from lattices is roughly as follows. So you start with the verification key, also known as the serial number, which is just a short wide matrix, and as well as a vector y, and they're both defined mod some modulus q. And the banknote is a superposition of short vectors x, such that a dot x equals y, again mod q. And note that we only consider single banknotes, but this is not a weakness because using standard techniques, you can always extend to multiple banknotes. So due to a previous work of Liu and Zandri, this scheme is insecure. And the reason is because of the following attack. So the attacker measures the quantum money state in order to get a short vector x. That solves the a dot x equals y. And now because x is now a classical string, the attacker can make copies of it, and specifically it makes two copies and pretends that both of them are the valid are the banknotes that the attacker pretends that both of these are the banknote. And Liu and Zandri showed that no verification procedure can distinguish these. No polynomial time verification procedure can distinguish these from the real banknote. And in more technical terms, this just means that the short integer solution hash function is collapsing. And what this means is that this attack is insecure. And the problem here is that distinguishing these pretend banknotes from the original, the valid banknote, requires solving the LWE problem, which is thought to be hard for quantum computers. One way that you might think to fix this is that you want to make the LWE problem easier. And a way to do this is by adding trapdoors to the verification key. And these trapdoors are just short vectors in the kernel of A. This is a common technique in lattice cryptography, and the hope is that we can use these for verification. And for example, the very recent scheme from Keshen, Liu, and Shor can be viewed in this way. And the contribution of this work is that any class of schemes that uses this kind of technique is still insecure. Note that the previous attack no longer works as is, because the trapdoors can be used to distinguish a single short vector from a superposition over short vectors. But this work shows that these trapdoors allow a new attack. And it goes as follows. So first we do as before, and we measure the states to get a short vector x. But this time we need an extra step. We use the trapdoors to create a superposition with shifts of x by multiples of the trapdoors. And a generalization of the Liu-Zandri result shows that no efficient verification procedure can distinguish this from the valid banknote. And And as part of showing this, the authors extend the Lewis-Andrew result to now work for any modulus Q, even ones that are not super polynomial. And what this means is that the recent candidate construction by Keshin, Liu, and Shor is, in fact, insecure. And along the way, they also improve some known results about the KLWE problem. So now, I don't want to leave you guys on a pessimistic note, so let's talk about some positive results. How do you build quantum money? So this work proposes a new framework called walkable invariance, and it goes roughly as follows. So the walkable invariance framework describes the following setup. We consider a set X over which the quantum money states will be defined, and an invariant I, which gives a label to each hash value, a label or hash value to each element. And these hash values, they sort of split the set into subsets, which have the same invariant value. And we then allow a family of index permutations on this set, but we require that the permutations maintain the invariant. In other words, the elements in the same subset with same invariant get mapped back to that same subset that has the same invariant. So in other words, these permutations, the invariant is invariant under the permutations. To define a quantum money state, we first choose a random subset with some invariant, let's call it Y, and then we take the uniform superposition over elements in that set to be the banknote. The invariant then becomes the verification key or the serial number. So now that these states can be sampled efficiently by the mint by just taking a uniform superposition over X and then measuring the outcome of applying the invariant. This framework also gives a way to verify the banknote. And that's by doing the following. So the first thing that we do is we test that the support of the banknote is contained within the subset of the proper invariant. And then second, we test that it is unchanged by acting with a random permutation. And this uses a version of the swap test. Note that the second test is what prevents the measure and copy attack that we mentioned earlier. And so the main theorem of the paper is a recipe for proving that walkable invariance structure gives a rise to secure quantum money. And for that, we need three ingredients. The first is a statistical property that a random walk defined by these permutations mixes. And then we also need two computational assumptions, which we will mention in the next two slides. The hardness of pathfinding and knowledge of path assumption. If the invariant satisfies all three assumptions, then this leads to secure quantum money. So the first computational assumption is the hardness of pathfinding. And that's that given 2 points in the same subset, essentially points that have the same invariant, it's hard to find a path that goes between them. A path here is just a sequence of indices such that the corresponding permutations map from one point to the other. Note that the mixing property means that there are many short paths between every 2 points. And the hardness of pathfinding just means that it's hard to find those short paths. And the second computational assumption is called knowledge of path. And before I say what it is, just note that given 1 point, it's always possible to generate a second point with the same invariant. And that's just by starting at the first point and then taking a walk along an arbitrary path from that point, and then you get to another point in that, within that invariant. But the knowledge of path assumption states that this is the only way to get 2 points with the same invariant. That is, any adversary that outputs 2 such points must know a path between them. And specifically, given such an adversary, we can extract this path. This framework can be applied to quantum money from knots, the proposal from Farhi et al. From 2012. The 2012 paper merely conjectured security, but gave no formal proofs of security. And in fact, before this work, little was known about its security besides just a general sentiment that problems dealing with knots are very hard. And so this framework allows us to formalize the necessary conditions for this proposal being secure. In this candidate construction, X is a set of knot diagrams under some encoding. The permutations are the set of Reidemeister moves. And the invariant is just the Alexander polynomial on that knot, which doesn't change when you apply Reidemeister moves. And so this scheme is this candidate construction is secure if the following three sufficient conditions, if these three sufficient conditions that we mentioned are all met. The hardness of pathfinding here is the pathfinding is just the task of finding a path of Reidemeister moves that goes from one presentation of a knot to another presentation of the same knot. And this is a known hard problem for knots. The knowledge of path assumption here is a new assumption, but it also seems plausible. On the other hand, it's unclear if the random walks mix. And even if it is true, it will probably be very hard to prove because it's related to the known hard problem of bounding the length of paths between knots. But in any case, these all seem possible, which means that this gives provable security of this scheme under some reasonable assumptions. Last thing I want to mention is that the paper gives some new instantiations of this framework, which gives some new candidate constructions of secure quantum money. The first instantiation is from supersingular elliptic curves, where the quantum money states are superpositions over these curves. The invariant is the number of points on the curve, and the permutations are the low degree isogenies. So the task of pathfinding here is the task of computing the isogenies, which is widely believed to be hard. The knowledge of path is a new assumption, but it's analogous to the knowledge of exponent assumption in groups, which is a very popular assumption, and it's plausible, but needs more cryptanalysis. And mixing follows from widely believed conjectures in number theory. And the problem that's missing here is that it's unknown how to create uniform superpositions over these curves, and it's related to the major open problem of obliviously sampling supersingular elliptic curves. So finally, the paper also discusses two other instantiations of the framework. The first from re-randomizable functional encryption, and the second from group actions taken with a classical oracle. Unfortunately, due to time, we don't have time to discuss them, but I urge you to see the paper for more details of these other constructions. Thank you.
So, do we have any clarification or easy questions for the speaker in the audience? Yeah.
So why do we use the supersingular graph? Why can't we do the ordinary graph of supersingular elliptic curves?
Unfortunately, this is something you'd have to ask the authors. I personally believe that it's a real thing, that we just need to construct it. But honestly, in order to be really convincing, I'd have to see the construction, and I'm also I'm hoping that we'll get there soon. The most plausible. Well, so the quantum money from knots that I mentioned is a plausible one. Unfortunately, proving the security of it is difficult. So if we can have more cryptanalysis effort on it, that would be a good thing. And these new constructions as well from these walkable invariants also seem to be good candidates, but unfortunately some of them have missing pieces, which hopefully will be solved soon.
Do you know if other group action will be considered, for example, for
I'm not sure, and you'll have to ask the authors.
All right. I think then we should move to the last talk of the session. And quick round of applause. The last talk is going to be from hardness of detecting superpositions to cryptography, and Minky Han is going to give the talk.
Hi, thank you for the introduction. I'm Min Kian from KIAS, and I will present the work titled From the Hardness of Detecting Superposition to Cryptography, which is based on the joint work with Tomoyuki Morima and Takashi Yamakawa. Okay, let me summarize the contribution of the research in just a single slide. First, we found some new quantum source to decision reduction. This is actually the theorem of a physicist, Scott Aronson, ITI, and Susskind. And actually, their theorem was motivated by something, I don't know, quantum gravity or quantum black hole. I don't know what it is, but we found that it is very simple and has a very interesting properties. And actually, since it is simple, and cryptographers already use similar idea in many previous works, like quantum Goldrich-Levin theorem. And we found further application to show that this reduction is really interesting. For example, we constructed the first public encryption based on the non-abelian group action, which was posed by TCC 2019, yeah. And we found another application to the quantum bit commitment for changing the flavor of a quantum bit commitment very efficiently and showing that essentially two flavors are essentially the same. Actually, the last result has some concurrent work recently. I think, Eurocrypt is cryptographic conference, but I think we need to start from some physical things. But I think you're all familiar with Schrödinger's cat experiment. In the Schrödinger's cat experiment, we prepare a cat and prepare some quantum atom, which with probably 1/2, it decays, and it is not decayed with 1/2 probability. And if atom is decayed, we kill the cat. Otherwise, we do nothing. So finally, we have a cat which is die or not. So if we believe the quantum physics, we have the cat which is simultaneously alive and dead. And if we refuse to believe quantum physics and we just use the classical probability theory, then this cat is live with probability 1/2 and dead with probability 1/2. And we can think the Schrödinger's cat experiment to ask if we can distinguish these two situations to determine we are living in quantum world or not. And as a cryptographer, we are particularly interested in if we can efficiently determine where are we. And believe me, this task is equivalent to the distinguishing these two states. One is the alive plus dead, and the other is the alive minus dead. Using some convexity arguments, some quantum physics, and believing this, our primary task is to distinguishing the alive plus dead and alive minus dead. And here the Arns-Naties-Hoskins theorem comes. They show that this distinguishing task is computationally equivalent to swapping the alive cat and dead cat. More formally, if we can distinguish these two states, then we can construct the unitary map U, which maps alive cat to dead cat and dead cat to alive cat. And yeah, we can say that in the above task, it is observing the interference between alive and dead, and in the task below task, it is a swapping task. And Arnson argued that if in the physical world we cannot resurrect the dead cat to alive, so swapping alive cat and dead cat is physically hard problem or necromancy hard problem, and this problem is equivalent to the distinguishing alive plus dead and alive minus dead. So, as I said, this above problem is equivalent to the distinguishing physical world and probability world. So, by using this interpretation, Aronson argued that observing the superposition in large state is computational hard because we cannot resurrect the dead cat. So let me talk about some formal statement of this theorem. Okay, we think about two orthogonal states x and y, and psi and pi is the x plus y and x minus y state. And for any delta, positive delta, these two tests is equivalent. The first one is the swapping, and the second one is distinguishing of x plus y and x minus y. And I don't want to describe the proof, but proof is really simple, just using some simple circuits. So why do we talk about this theorem, this physical theorem? Because we found that this theorem can be interpreted as a quantum search to decision reduction. For example, let me describe more detail. In the above test, it is kind of a search test to find x from y and y from x. And if we set y to be fx for one A function f, then this test is to find x from fx, which is one-way hard. And the second task is apparently distinguishing task. And this theorem says that these two problems is equivalent. So it can be seen as a search to decision reduction. Yeah, and we know that search to decision reduction is very important in cryptography and computer science. For example, for the satisfiability problem, we usually define it as a decision problem, but we usually want to find the solution of satisfiability. And in cryptography, we usually assume the minimal assumption like a one-A function, but we at some point want to prove some decisional hard problem. So we need at some point search to decision reduction. So I think it is our main message. Their theorem is a new quantum search to decision reduction. And as I said, we found that this idea is already used in many cryptographic works like quantum Goldrich-Levin theorem and some recent work on collapsing, and some our follow-up works like public key encryption from one A function, quantum public key encryption from one A function. And we found some new applications, like, yeah, as I said. I think I have to hurry. So we need to talk about cryptographic application. The first one is the public encryption from non-abelian group action. And the second one is efficient flavor conversion of a quantum bit commitment. And now we are going to cryptography, but we need to go some details. Okay. Non-abelian group action is defined for group G and ZS. And it satisfies these two conditions. For the identity element in group, it maps Z element to the, it acts as an identity map, and it satisfies GHX to, is equal to GHS. And we say that group action is one way if it is hard to find given S and GS, it is hard to find G. And we say the group action is pseudo-random if S and GS is computationally indistinguishable from S and T for random T. And if we assume an abelian group action like isogeny, then we can simply construct the Diffie-Hellman style key exchange easily. But recently in TCC19, researchers suggested the non-abelian group action as a new cryptographic primitive, and they constructed some mini-crypt primitive, but they cannot achieve public encryption, and it lives as an open problem. And we did it, but I wait with quantum ciphertext. As the construction is simple, we talk about it in detail. The main idea is this: just using the Aronson-Atiyah-Susskind theorem directly and encode bit in phase. More precisely, our ciphertext is of the following form. For Z element S and group element G, we construct some ciphertext of B to be something like that. Encode the bit in the phase. Then, if we constructed this ciphertext, then Aronson-Atiyah-Susskind theorem says that distinguishing these two quantum states is equivalent to mapping S to GS, which probably says that we know G, which breaks the one-wayness of a group action. So it is a basic idea, but there are many problems. For example, it is hard to construct from what is secret key and what is public key, and it is hard to construct, and it is hard to distinguish. No, never mind. So we come up with some other complex construction, but it turns out that it is easy to construct from secret key G and public key S and GS. And we show that if underlying group action is pseudo-random, then it is in CPA secure. Okay, before move to the commitment, I need to talk something more about the equivalence theorem. As shown in this simple proof, we can observe that this equivalence theorem preserved have some interesting property like locality preserving, which means that if the map A do not act on some qubits, then you also do not act on the same qubits, and vice versa holds. And we show that this theorem holds even if we have advice. Okay, then let me talk about bit commitment. In the bit commitment, there are two participants. One is sender and the other is receiver. Sender wants to commit, he decides bit B, and using the commitment, in the first phase, in the simplest case, in the first phase, it is sending a commitment, and later it sends the opening to convince that he choose B. As we have two parties to define secret, it's too short. Okay, it has a two security notion. One is hiding and one is binding. Hiding says that sender cannot change his mind after commitment, and receiver cannot find bit before opening. And we essentially want that they are statistically held, but it is shown that both are statistically held is impossible, even in the quantum world. So in cryptography, we usually relax one of them. There are two commitments. One is a statistical hiding and computational binding, and the other is a computational binding and statistical hiding. And in the quantum world, in the quantum world, it turns out that quantum communication is very helpful for commitment scheme. It is shown that there are simpler constructions for quantum commitment, and it is shown that quantum commitment is inherently non-interactive. And it can be described as a simple protocol, like sender prepares just two register quantum state and send register C as a commitment and send register R as a opening. And recently, Jan shows that there is an efficient conversion of a flavor. In classical setting, it is technically possible, but very complex to change the statistical hiding to statistical hiding, computational binding to statistical binding, computational hiding. But in the quantum setting, the conversion is much simpler, has a multiplicate overhead lambda square. And we show that it is essentially equivalent. Just calling a single statistical hiding computational binding commitment can make a statistical binding computational hiding commitment. Yeah, the idea is simple, but idea and proof idea is actually simple, but just skip it. Okay, our compiler is like that. If our base commitment is if our base commitment construct phi 0 and phi 1 as a commitment of 0 and 1, then new commitment scheme is just like that, and changing just the role of C and R. It works as changing the hiding and binding. Yeah, and it has a concurrent work recently. So let me wrap up my talk with conclusion. We found the new quantum search to decision reduction based on the physicist theorem. And we show that it has really many applications, like one from PKE context and the other is in the commitment context. Thank you for listening.
So, do we have any questions? No questions?
Yeah.
I think, thank you again.
Thank you.